we can't quite see the Big Bang, but we basically look back in time. And we've learned a lot about Big Bang nucleosynthesis. We've seen and picked up on the cosmic microwave background, which is basically leftover sort of photons and light in the microwave wavelength that's hanging out from when the universe was 300,000 years old. So this kind of looking back in time not only gives us sort of a look back in time, but also it means that you're going farther and farther away from us, right? And learning more and more about this universe that we know and love. How much we know it sometimes changes, and how much we love it, well, that's subjective. But let's see what the author says, turning back the clock. The production of the microwave background during the epoch of recombination. So by the way, this epoch of recombination, that's the time. So another way of putting all of this stuff that I was just now saying, turning back the time or turning back the clock, is the universe has gone through evolutions. What the universe is up to right now is different from what it was up to a few billion years ago, maybe, and especially different from what it was up to early on in the universe, right? There were no galaxies early on in the universe. There were no quasars. There were none of this stuff. So quite different things were happening in the early universe. And so we've kind of named the epochs differently. So this cosmic microwave background radiation that I just now mentioned from 300,000 years old of the universe, when the universe was 300,000 years old, there is a cosmic microwave background radiation that we can still pick up on. It is actually everywhere. It's very homogeneous, very isotropic. No matter in what direction you look, you see this. That's from this epoch of recombination, okay? So the synthesis, that and the synthesis of the elements during the nuclear fireball are two major successes of the Big Bang theory. So this is the Big Bang nucleosynthesis that this person is talking about. This author, Peter Coles, is talking about. Big Bang nucleosynthesis basically gave us hydrogen and helium and very trace amounts of lithium. Every other heavier element was made in stars after stars became a thing, right? Before the stars were even a thing, the universe gave us hydrogen and helium, a little bit of helium, and even smaller amounts of lithium. And that is basically Big Bang giving us that. It's nucleosynthesis associated with that early time. The way observations tally with detailed calculations provides firm support for the model. So that's the other thing, that the Big Bang has some firm support supporting it, because some evidence is supporting it, because even now when we measure these things of how much we expect of what in accordance with Big Bang, we actually get the confirmation. So the way observations tally with detailed calculations provides firm support for the model, buoyed by these successes. I always have trouble with that word, buoy, B-U-O-Y. Cosmologists have since tried to use the Big Bang to explore other consequences of matter at very high density and temperature. So another thing is, of course, at this point in the universe, it's not as high density and it's not as high temperature. When the Big Bang was happening and when the universe just got started, it was a very hot, dense, high temperature environment, very different environment than what we see now. Okay, it was called radiation dominated environment. Lots of photons, electrons, positrons actually were sort of in that cosmic soup, if you will, and lots of hot, dense, just crazy stuff going on. We wouldn't have been forming at that time. We are part of the now or a much more current universe. In that past, it was very different. Okay, very, very, very dramatically different. So in that very high density, high temperature environment, in this activity, the Big Bang exploits the connection between the world of the very large and that of the very small. So this is another thing, is that because the environment then was so extreme, it's almost like the Big Bang has this ability to unify the world of the very small and the world of the very big, because the very big was part of the very small at that time. The universe was smaller then, right? The length scales were different. It was hot, dense, temperature, high temperature, all not expanded as much as we are now. So it's almost like everything was part of that same cosmic soup, that it's like everything is more unified at that time. So Big Bang, in other words, is a model that's kind of exploiting that, well, things could have been very, very unified back then, and things are, of course, very different now. So it's almost like a way to explain it away, if you will. The further into the